Start. Good afternoon. I'm Sharan, and today I'm talking about DPDK Unikernels with Unikraft. Before we go into the topic, let me just introduce our group. We are part of an 8-member team from NEC Labs Europe, and we are part of the systems team inside NEC. And this work contributes towards Unikraft. So before we go into the topic, just give you a brief overview on what it is. We begin with what we saw out there, and then we introduce Unikraft and what is the motivation behind Unikraft, and then how we fitted DPDK into Unikraft, and then we move into how to fit Unikraft libraries into DPDK, and then discuss about the synergies of the two projects and why we believe it makes sense to support DPDK on Unikraft. Before we get started, how many of you here are aware of Unikraft? Not a lot. About Unikernels as such? One of them, OK. So it's a new topic, then probably it's a good refresher. So when we started, what we started with looking at what was available. What was available was we traditionally had guest OS and a hypervisor like KVM separating it, and you can have established communications between the guest OS and the hypervisor using something like a VirtIO scheme, and where they can exchange information. And then DPDK went ahead and implemented a new version called vhost. But from our perspective, there's one part which has been left untouched, which is the guest OS. And we believe we can specialize the guest OS. And I think the number of projects out there recently which have been trying to specialize the guest OS as such. By specializing what we mean? We mean is we only pick components we need for the application, thereby optimizing for image size as well as boot times. And if we are focused on making it just specific for one application, then we believe the isolation existing within the guest OS is probably redundant, because we already have a single application running, and so for us it doesn't make sense at that layer. So let's start a discussion here. So when we get the first thing we get into is we make comparison between a virtual machine and a Unikernel. A typical virtual machine, what you have is a Debian image as a guest OS with a KVM hypervisor running in between it. And then you have a generic management interface where you request devices, request and share resources among the different applications running within your virtual machine, or the management interfaces. Whereas with Unikernel, what we try to do is we just build it for one purpose, which is specifically to do that specific application. And with that in mind, what we can optimize is for the use case. Knowing the use case, we can improve and optimize our Unikernel for that specific use case. When we mean that, what does a Unikernel really look like? What we do is essentially, we have something like a minimal kernel embedded into the application. So then you have a thin layer of then the application developer, depending on his use case, picks and chooses whichever kernel primitives he needs and builds it into a single application image, which has both the kernel libraries as well as the application code running there. Would that mean that what does it mean with respect to the memory map of your process image itself? What we have is all the memory separations between the kernel mode and the user mode is all removed. And everything, your application basically runs in ring 0. And the advantage which we gain with this is we could specialize on each of the layers in the stack. We could pick and choose whatever we want. And that's the benefit we gain from optimizing it for a specific application. And the next thing is, where do we realize it? Right? For example, the benefit of a Unikernel is a fast instantiation time. What we gain with that is, for example, one of our publications on LightVM, we published that we can spin up a unikernel in a matter of 3 milliseconds. And it minimum of 3 milliseconds, and if you start spinning up more unikernels, it goes until maximum 700 milliseconds, which was about for 8,000 odd unikernels running inside a single machine. And the other advantage is it's very minimal in size. What we typically have is, if you have a Debian image, it's about 1.1 gigabytes in size, whereas an Alpine is probably a few hundred bytes in size. Whereas in our case, we make unikernels. A simple unikernel can be built at a minimum of 30 kilobytes. An entire virtual machine can run within that image size. And the advantage with that is we have a very high deployment ratio. For example, we prove that we can pack about 8,000 unikernels within a 64-core AMD system. And the next is, in terms of performance, what we gain is, it's a research publication where we showed that we can match 10 gigabit throughput rate, that's a 2017 publication when we are not further tested it yet. But what we also observed was, in terms of processing user request with a unikernel, what we could do is we were going until 600K requests per second on a single core, whereas a modified Linux kernel stack could only process around 118K requests a second, and the off-the-shelf would be around 85K requests a second. So, and the good part about it is, as we scaled on different cores, we were able to scale more. We were able to process more requests. So, and the last advantage which we get is in terms of security. Since it's a small, it's a twofold improvement. One is, since it's a small code base, the attack surface is small. And also, in terms of comparison, we don't have any a syscall interface. We just have a hypercall interface, which is smaller than a syscall interface. So the attack vector is also quite small in that sense. So when you say unikernels, you seem to say that it gives you high performance, it gives you good isolation and less attack surface, and it gives you faster instantiation time. But it has not quite caught up. There are a number of reasons why that is the case. Because what it takes is, it takes quite a bit of a development cycle to get a unikernel, build a unikernel, right? And also, we have had experiences where we had to build unikernels for specific use cases, and then build a similar unikernel for a separate use case where we couldn't generalize it yet. And then the other aspect of it is, when you're specializing, you need two control of it. One is you need a way to specialize, to say you need specific libraries, and you need to pick and choose the kernel primitives. So you need build tool support on making sure that you can select whichever components you need and deselect whichever components you don't need. And also, the separation of interfaces is quite difficult to get it right. And there's also the other component, which is always balancing between specialization and taking an off-the-shelf application and running it. So when you take off-the-shelf an application, then you have expectations on certain level of what the application expects. You need to satisfy, say, a POSIX API or something on that layer, so that off-the-shelf application can run on top of a unikernel. So this is something which was not working for us, so we decided to come up with a tool. So when we started with the project Unikraft, we had some use cases in mind. One of the topmost priority in our mind was to get reusability into the picture, because we burnt our fingers doing that one. So what we tried to do is try to construct basic components which can be enabled and disabled depending on your application needs. And then we added necessary build tools for you to express the relationship between different libraries and how to track dependencies across different libraries and an application. And also, what we wanted was, we needed to support a wide range of platforms. Platforms meaning different hypervisors was also on our card. And what we wanted was different CPU architectures also had to be supported. And what we also needed was the base functionality which is needed for a Unikernel should be very minimal. So if you build a Unikernel, this is the bare minimum you need. That was quite small in our case. So thus, with this, we came up with a project with this Unikraft thing where every component which we call as base component is a library. And almost all of these generic operating systems primitives are combined as these libraries, and they can be enabled and disabled. And then what we classified in Unikraft was two large groups. One was the library pool and the build tool utilities itself. And this build system also gave us the capability of establishing this relationship between the different libraries as such. And the project is open source under a BSD license. So if you want to try it, you can always try it. So next, what we do is we just go through a run through of how porting an application into Unikraft looks like, right? So we just take an application, for example, a Python application or an L2 forward application. And then each of these applications has a list of dependencies. And we need to make sure that we select these dependencies. And these are the main pool of libraries. An example of this main pool would be a boot library. We can customize our boot library, by which we mean we can statically partition our resources for a specific application and hand it over using the boot library as such. And then also you had libraries which does these OS primitives. For example, those block devs, console devs, and net devs. It lets you implement all these interfaces on top of these libraries for different device use you need. And then we had support for different multiple language runtimes, whereby you can build Unikernels with different language runtimes like Python, Go, or Rust, or whatever we support right now. And these libraries, these belonging to the main pool, are independent of the platform. It can run on the different platforms we support, which are, for instance, we support our Unikernels running on KVM. Linux user space is just an application running on a Linux kernel. And then we have Zen, and we have Firecracker support. Also, we have running on hypervisors like Solar 5. And also, we have a bare metal implementation, which is capable of just booting up right now. And apart from that, there were also these driver supports, which are very specific to a Unikernel, which were part of the. And with that, you build that application, select your architecture, and build it for the different types of architecture you want to support. So with that in mind, this is how we pictured when we started our porting towards DPDK. This is how we visioned it would be like, right? So what we had was, we had a DPDK application running there, and then we have a glue code, which is the lib UK DPDK there, and then the different libraries which DPDK requires, for example, pthreads and intrinsics, and if you need some file system support, then you have the VFS core running on top of that one. And this is not a comprehensive list, but it's just to give you a mental picture of what we thought of. But we wanted, but also there were some challenges which we had in mind to make sure that we can get it working with DPDK. What were the challenges were, the advantages of both the projects were it was quite modular. So you can plug and play whichever libraries you need from DPDK into Unikraft, but the build systems were not compatible. So we needed a way to make them understand one another, right? And then the idea behind that one is then we can make upgrade of newer versions of DPDK also easier, because then we understand the build system and we can take whatever is there in DPDK and then use it, right? And then the next point of focus was, how do we specialize the Unikernel as such for this DPDK purpose? And then we thought about some use cases where we can where our project helps in this case. And the third obvious case was never change anything on the upstream code, so that it just takes time to get your entire process through, right? So to address the first challenge, what we had was we had something like kconfig-based system, which is from the Linux kernel. You all might be familiar with it, where you have a way to establish dependencies and relationship between the different libraries using, say, for example, a depends and select and calls within the kconfig system as such. And whereas what DPDK had was a set of default configs where you have to pick and you can configure your application. And apart from that, you had set of CPU flags which were compile time generated, and that we added into Unikraft to support that one also. Then there is a need for translation between DPDK variables and Unikraft variables. These are, and the final part was the way of visibility between the two projects. So which are all the global available functions and how to mask them between libraries. So we had something like an export sims, and DPDK had something like a version map. So that was sort of a one-to-one match there. So what our proposal was, like everything else in Unikraft, was to come up with a build tool utility. What it does is it pre-processes all the makefiles of DPDK and makes it available in a Unikraft understandable format. And all this was written inside with the help of make. And with this, what we gained was we were able to maintain the internal structures, library structures of all the DPDK libraries, along with the libraries which Unikraft supported. So it was quite a modular image as such. And then from the DPDK application perspective, what we have is there's no change because you had all these libraries always available in Unikraft, and you can just plug any application which runs on, say, DPDK can be run on Unikraft without any much change here. And finally, as I mentioned earlier, updates to a newer version of DPDK was quite easier. For example, we were able to go from 1804 when we started our porting to 1908 without much hiccups and stuff like that. And so this is how they finally turned out into. What we had was we had a DPDK application, and we had multiple DPDK libraries around it. And what we needed was an implementation around UK ring and UK pole mode driver, because we needed some levels of translation between Unikraft world and the DPDK world, which is something which I'll discuss in the next few sections. And also we added some implementations around EAL, which is Unikraft specific, and that also I'll discuss it next. The first phase, which is the EAL support, we thought it is possible the primary motivation here was to specialize the guest OS. And what we thought was we can gradually, as well as simplify all the interfaces around the device management for the application devices as such. So what we decided to do here was we classified it into 3 use cases where we can specialize. One was on the memory management side, and the second one was on the device and bus management, and the third one where we thought we could make sense is in terms of CPU isolation and interference from the different cores. So what we decided to do was go through one by one. In terms of memory management, what we have with Unikraft is we have huge page-based page tables, which are 3-level hierarchies. And what we have is we map a single Unikernel with about 1 GB of memory, and we hand it over to the application, and the application is up to it to control the entire memory space. And then there's a one-to-one address map range between the physical and the virtual memory as such. And from the application perspective, since the memory region is reserved for itself, it knows what to do with it, and it can implement an allocator on top of it. For example, a heap alloc on top of it, and it can hand out memory to the way it wants it to customize it. And the next thing is about device management itself. In terms of device management, what happens with Unikraft is whenever you find a device, Unikraft just hands it over to the application, and it's up to the application to just manage it. So once you have a network device identified, it just hands it over to your DPDK libraries. For example, if ETH dev to handle the ETH device as such. So we don't have any interference as such from that perspective. And finally, in terms of CPU scheduling itself, currently we just support single core. But what we could do is we have a scheduling library, and what we can do is we can also remove the scheduling library, and you can handle individual vCPUs to the individual cores and let it take care of the entire scheduling. And we can just give you a minimal implementation to just set up your stack and start running your application on top of it. So it is as minimal as possible in terms of a vCPU perspective. But then we ran into this problem of having interfacing between DPDK and Unikraft as such. So typically, what we had with DPDK was we had a burst operation, and then it goes into the ETH thing with mbuff buffers, and that performs a burst, and this goes into the device. Similarly, what we had at Unikraft is something called net buffs, which was an equivalent structure around mbuff, and we needed to make sure that if there is a crossover from DPDK libraries to Unikraft libraries, we needed to make sure that the net buff and the mbuff can interoperate with one another. So what the structure of this looks like is something like this. So you had this DPDK object header, and then you had mbuff, and then they had the payload around it. Similarly, we had with Unikraft, what we had is a netbuff structure around it and a private data around it. And then we had a leeway for adjusting the headers around a packet and the trailers around this packet. So how we combined it was to make sure that we have netbuff. We have the netbuff embedded after the mempool header, and then you had this private data of the netbuff pointing into the mbuff, and then you had this packet data around it. So why did we adopt this approach? Is we had multiple use cases. One is we wanted to make sure that we could try out DPDK libraries on top of a Unikraft driver. So in such a case, we needed a translation layer from mbuff to netbuff. Similarly, if we wanted Unikraft libraries to talk with DPDK drivers, we had a similar level of interfacing we needed. So we came up with this approach to address that problem. So this is a work in progress. Right now, we are trying to evaluate the performance and support multiple cores as such, and try to add DPDK drivers directly working on top of Unikraft. If you're further interested, there are some set of links. You could check it out and try it out by yourself. It's all open source. And to summarize, what we think is, from Unikraft's perspective, it supports multiple platforms. It can specialize for guests in terms of it provides you a simpler device management interface, and also it provides increased control for your application. And in terms of DPDK, what we get is a specialized network stack, and we have a high-performance network stack, and from the driver's perspective, we have a very good knowledge on the wealth of the knowledge inside the DPDK drivers, which we can use it with Unikraft and then we have an increased application base. So this is why we believe the two projects are in synergy, and we can exploit the synergies of the two projects together. And that's the end of it. If you have any questions, I'm ready to take it.
Hi. I think maybe Kata container can use this, because Kata container also use the lightweight VM. Right? Maybe this Unikernel is lightweight.
Yes. What we have is we also have even minimal in terms of kernel components itself. It's bare minimal, so it's even smaller, I guess, with Kata container, I think.
Okay. Another question is, Do you have data for Unikernel image size for your DPDK application?
Sorry.
What is your Unikernel image size for DPDK application?
Right now, it's about, I think it was few megabytes in size. I don't remember the number from the top of my head.
Okay. How
because we are evaluating it yet, so we are still working on it. So that's some, so we are not yet optimized it to the maximum, so to give you the correct number as such. So just few megabytes in size.
Okay. How about boot time?
Boot time as such was 3 milliseconds without the initialization. Just the platform boot time is about 3 milliseconds to get it up and running.
Okay, got it. Thank you.
Hi,
Sure.
I just have a question.
Sure.
So when you are saying building an Unikraft application, so basically you are putting all the library pool and guest OS into together with the application, right? And then in the end you are building a guest kernel image, something like that.
Exactly. It's a guest kernel, which is a virtual machine which you can run it. So it's your application is running in ring 0 without any kernels as such. It's a hypervisor interface between it.
So isn't that a lot of change in the guest OS? I mean, you mentioned about memory management, CPU scheduling. So I assume it's a lot of change in the guest kernel, guest
yes, exactly.
OS. Oh.
It's only within the guest we're talking about, not within the host part.
I see. I see. Okay, thank you.
Hi, I'd like to ask a question about the memory pool. So you mentioned that you customize the memory pool for the smaller memory footprint.
Yeah.
So how do you do that?
What we did was, in terms of memory pool itself, what we mapped is, you mean to say memory pool of the entire application or the VM's memory?
I don't know. Maybe both for application or the whole platform. You need a memory
So
pool, right?
what we get is we set up the page tables and we set up the initial 1 gigabyte of memory within the first into our page table and hand over based on what we need just for. So the boot library itself has the capability to customize it and statically assign different memory regions to a memory pool.
But DPDK memory pool now need to pre-allocate, need to populate all the memory for once, right? So how do you do that for?
Right now we just support 1 gigabit. So that's our.
Okay, I see.
And we are planning to extend it further. So that's work in progress rather.
Okay, we may have some progress on that, and we may have a talk tomorrow. We may discuss more about this offline.
Okay, sure.
Okay.
That'd be nice.
Okay, thank you for the talk.
Great. Thank you.
Thank you.
Thanks.